Hello everybody, this is Dr. Hassan again, Electrical and Electronic Circuit Analysis. We're still working in Module 3, Diode and Transistor Circuit Analysis. I will start with the transistor, which is the first type of transistor to discuss in this course, the bipolar junction transistor. Let me start from principles. I will take you through the concepts and then BJT principles, BJT characteristics, BJT load line analysis, where we are going to see the principle, circuit application and formula. History take me back to the valve. Around 100 years back, humankind been using valves to do the function of control on off and switching, let me say, or amplifying sometime, okay? And you can see here, you may not find this available in the market today because history, you may find them in the museum anyway, or some university they keep some for show their students. And here in a board, small board, you can see the size they take, and just a few of these valves can do the function. There is what we call the triode also. This is how it look like, the circuit. I'm just showing you the history. On these three scientists, talking about Shockley, this is the old man, and Berdeen and Aberdeen, these three scientists from US, they discovered in 1947 the transistor, which totally changed the humankind lifestyle, and everything changed. This is a crucial point in the in the history of humankind, where they changed everything. Everything changed from mechanical situation, where the world was moving in the direction of mechanical, into electrical and electronic by inventing this transistor. This is the first transistor they invented, and they won, by the way, Nobel Prize. And you can read about these scientists and how much their effort give push to the technology we are using today. Now, one of the application we are going to focus on, this is example, just otherwise there are wide number of application. You see this one? This you may say, okay, what is this one? You have never seen it. It's actually radio and amplifier, okay? It's, let me say, the first version of iPad. Talking about tens years back, humankind have been using this one to amplify signal. We have microphone, we have a speaker. We speak in the microphone, we say hello, it go to the transistor, definitely where it supplies. It become, you see, large hello, okay? This is amplification. Also, since we are talking about history, in 1958 they started, let me say, manufacturing the first integrated circuit. See how it looked like at that time. It contained many transistors. This is also printed circuits in the past, but see today, this is the past. See today how it look like. They have billions of transistors in small chip, 3-terminal device. What we have here in this device, we have collector, which is simply C, base B, emitter E, emitter base collector, okay? And there are two different type, 3-terminals device. There are two different type of BJT, bipolar junction transistor, PNP and NPN. You remember the layers P and N, P positive layer and negative layer. We either put two N layers and one P, we got NPN, or we have two P and one N, we have PNP. Now I don't need to repeat the same discussion for both of them. I will focus on NPN, otherwise PNP is the same, just the sign, the direction are different. Okay. Now what is the symbol for transistor? Symbol for transistor, as you can see here, in this way, this is the base, and this is line going outside. Okay, this is collector, this is base, this is emitter. This is how it look like, the symbol. And frankly speaking, this transistor actually, it's represented by two diodes opposite. Okay, diode in this direction, diode in this direction. This is base, collector, emitter. Okay, NPN. And the opposite direction for a row for PN, and the direction of face to face for diodes. Okay. Now how it work? I will show you here in this example, when water coming from here, and there is a small valve, okay? And here is the base. This is the collector, this is the emitter. It's for water. I'm checking here, discussing here for water. When we have small water coming to push this gate up, more current will follow through the gate because it's opened. Now the same principles applied here. With a small signal coming to the base of the transistor, we can't have amplification for the signal. The small hello become big hello. Okay, now this is a symbol for MPN. This is the base, this is the collector, this is the emitter. I emitter following through the emitter, I collector through the collector, I base through the base, and the point here between this point and this point is the voltage, which is V collector emitter. Okay, now for the transistor to work in the forward bias, two conditions need to be satisfied. The first condition is V base emitter between this point and this point, which is usually 0.7, as I mentioned always, 0.7 for silicon, 0.3 for germanium. Many of the, almost the transistors used today are manufactured from silicon-based technology. So the V base emitter should be in the forward direction, forward bias, as you can see here in this graph. And you know what is the meaning of forward and bias and reverse bias. We discussed it in the topic for diode. And the second condition is V base collector, the voltage is here, between here and here, is reverse bias. So if V base collector is reverse bias, V base emitter is forward bias, the transistor on stage. And what happens is, when we apply, this is here the PN junction, you can see here this is N layer, P layer, and another N layer. In N layer we have electrons in the outer band, in P layer we have here the holes. Okay, now when we put positive negative, okay, here voltage between base and collector in the opposite direction, we make attraction for n-type here down, so it be increased down here. And when we put another voltage for between base and emitter, we circulate current. It's like ball falling from hell. Okay, so from up and down, and it's working in this way. If you remember in diode circuits, we mentioned to the Shockley equation. This is the Shockley equation. Okay, so if we assume that the diode or diodes represented by our transistor by two diodes opposite, okay, so each diode, as example, this diode is the emitter here, base here, collector here. The current following here can be represented by Shockley equation, and I will call this IE and this is VBE. Okay, now the highest current in the circuit is I emitter, which is combining of I collector and I base, because here and here, according to Kirchhoff current law, they are combined. And the difference between I collector and I emitter is the I base. So if I divide I collector over I emitter, I come up with a parameter, I call it alpha, okay, which is the ratio between current in the collector and current in the emitter. Now usually alpha in the range of 0.1, never reach 1, 0.999, 0.99, and so on. So if I substitute in the previous equation here, okay, and simplify, I get I base with respect to I emitter now, which is very small. It seems to be I base is a small fraction from I emitter because it's 0.01 or less even. Now if I use the same Shockley equation for I collector, which is I emitter times alpha, okay, this is I emitter, I mention it, then we have this formula. Okay, now V base emitter, as usual, we equate it to 0.7, and if we assume that there is -1, this -1 to be ignored because it's compared with this part is small, then this is the approximate formula. Okay, and IS, okay, equal alpha ISE. Now have a look here. Now I emitter, we mentioned it is I collector plus I base, and I base is I emitter minus I collector. Okay, and since we can't take I emitter because I collector here, remember I collector, we say I collector over I emitter equal alpha. So substitute here and simplify, then what we have alpha 1 minus alpha I base. So we have formula now for I collector, I emitter, I base. Now let me define another ratio, which is beta, which is the amplification here, which represent I collector with respect to I base. And if we use the formula of alpha, then it is alpha over 1 minus alpha. Okay, usually beta is 10 times, 100 times, 1000 times, and so on, because you know the I base is small, I collector is larger compared with I base. Okay, you see 10, 100, whatever, 200, 700, 150, and so on. And I collector is beta I base. Okay, it means amplifying I base by beta. Now let me summarize this formula. This is I emitter, this is I collector, which is alpha I emitter, this is I base, which is 1 minus alpha I emitter. And alpha defined to be IC over I, which is less than 1, and beta is IC over I beta, which is approximately 100. The relationship between beta and alpha can be represented in this formula or this formula. As you can see here, this is I emitter, most of it coming from I collector, a little bit coming from I emitter. Let's take example. A certain transistor has beta is given, IES is given, which you see is minus 14 small. VC is given, IE is given, V thermal is given, which is 26 millivolt. He asked me to find V base emitter, V base collector, I base I collector, and I emitter. Okay. Now, from the formula, this is the formula, okay? Approximated from minus 1 has been ignored, okay? So, IE is given in the question, IES, and IE is given, VT is given. Can we find VB? Yes, we can. You see, 718 millivolt, it's around 0.71 volt. Now, V base collector is V base emitter, we already got it, minus V collector emitter, which is also given in the question here. So you see it's in minus, which tell me that it's reverse bias. This is what we say. It's supposed to be reverse bias, so the transistor will be in the forward bias. And we can find alpha since we have beta. We got it. We have formula.